Today, we're going to start with Newton's method. And we're going to draw a pretty picture. Here's a function. Here's the function f of x. How do y'all like that function?
That's a beautiful function.
Thanks. That's what I felt about it.
Very curvy.
I bet it takes in input values and creates output values really well.
No, not this one, but that's okay. All right. What I want to know about this particular function is what its x-intercept is. What's its x-intercept? Who knows? It's this value right here. Well, I don't know what it is. So what I'm going to do is I'm going to take a guess. I'm going to guess that, oh, geez, I'm not very good at this. I'm just going to blindly go out here and guess. This is the x-intercept right here. Was I right?
No.
No, I was wrong. I was wrong. Let's see. So what I could do, though, is that since I know what I guessed, I could go up here and find the value of my function there. Let's say we called this x naught. This would then be the point x naught comma f of x naught. Oops, f of x naught, right? Not f sub x naught. True? Would you agree? That's x naught f of x naught? Yeah, good, okay. Could I find the derivative of some function at this point?
Yeah.
Yeah, and if I did that, its slope would be whatever that derivative was, right? And we should be able to then, oh, that was really bad. We should be able to write an equation to represent that tangent line there. Yeah?
I bet we would.
I bet we could. It would have a slope of f prime, right? X naught. And its equation would be, let's see, y minus f of x naught equals f prime of x naught times x minus x naught. Yeah? Everybody agree with that? That looks like Ryan's trajectory for his bike rides, right? Just straight up almost, right? That's all you do, Ryan, is ride straight up hills.
Yes. Sure.
Perfect. All right. This line has an x-intercept, right? Everyone agree with that? That line has an x-intercept?
Yes.
Yeah, let's call it x1. All right. Is it a better approximation for this x-intercept than my original guess was?
Yes.
Yeah, most definitely, huh? All right. Could I find the value of x1?
Yeah.
Yeah, how would I find the value of x1? I'd call this thing x1 and then plug in 0 for y, right? So we would have x, well, we'll call this, we'll say 0 minus f of x naught equals f prime of x naught times x1 minus x naught. And we could find x1 by then just dividing by f prime. So we'd have negative f of x naught over f prime of x naught. And then we'd bring the x naught over here. X naught minus that would be x1. Everybody agree with that? That would be the value of x1. Yes, no, maybe?
Yes.
Wonderful. But this wasn't our x-intercept. So let's go up here. We could find this point, right? Wouldn't that point be x1 comma f of x1? And it's got a tangent line. Oh, that wasn't very good. It's got a tangent line. That wasn't very good either, especially since it didn't really. There we go. That looks nice. There's our tangent line, right? And we could find the derivative of that tangent line, right? Or the derivative of the function at that point, right? F prime of x1. right? We could find the slope there. And we could write the equation. It'd be like y minus f of x1 equals f prime of x1 times x minus x1. And we could probably then say that that had an x-intercept and find that x-intercept, couldn't we? And we could call that x-intercept x2, and that x-intercept would probably be x2 is equal to x1 minus f of x1 over f prime of x1. True? I hope so. And that x2 is a better approximation for this x-intercept than either x0 or x1 was. And then we could go in and we could say, oh, well, there's the point x2 f of x2, and it's got a tangent line. Gosh, that's getting even better, isn't it? And we could just keep doing this process over and over and over again until we were as accurate as we wanted to be with that x-intercept. True? This is called Newton's method for approximating intercepts. Pretty cool, huh? Yeah, it's a lot of work unless you can make your calculator do the work for you. So this is how Newton approximated x-intercept. This is how x-intercepts are approximated using your calculator. That's what your calculator does behind the scenes when it approximates x-intercepts. And we want to know how to use Newton's method to approximate them. We see the process, and we would just go until we had as accurate of a response as we wanted. Everybody okay there or no?
Yeah.
All right. So our process then is to basically use this little formula each time, right? The next guess is equal to the previous guess minus f of the previous guess over the derivative of f at the previous guess. And so what we've done is we've taken an initial guess, then we use the tangent to the curve at that point to find the next zero, and then we use that as our next estimate and just repeat it and repeat it and repeat it until we are as accurate as we want to be. Newton's method. So everybody okay with the idea of Newton's method and using this formula for it?
Why is it that for every function that has an x-intercept, like x sub n plus 1 is always going to be closer than x sub n if you use this method?
Well, it's not always going to end up working out. You have to pick something that is sufficiently close enough to it so that there isn't like something weird going on in between there. Like some functions, like let's say like the cube root of x or something like that, or like the cube root of x plus 1. Based on the nature of that, if you pick something that's a little bit too far away from the actual value, it ends up getting you further and further away from it just because of how that function is drawn. But generally, it's because of the curvature of these functions that we are able to get closer and closer to it. Because if we have something that's concave up like this, right, all of these tangent lines are getting less and less steep. They're getting more and more like they're getting to be more and more like what the function, how the function behaves at that x-intercept. And the same as if, we had a function that was doing this, well, each time we picked one, we'd be getting something that was steeper, which is getting closer and closer to how the function is behaving at that x-intercept. Does that make sense or no?
Yeah. If it were to like switch from like increasing to decreasing or decreasing to increasing in between the value that you chose for x0 and the x-intercept, then would it still work?
It might and it might not. It just sort of depends. So that's one of the things that can affect it. So like, if we have something like this, let's say, it might eventually still work, but it also might not, just sort of depending on how it works. So suppose we chose this first. Well, this tangent line sucks, right? That was really bad. We get something over here, we go up here, and it's like this, and then it comes back this way, right? Well, there's our next guess. It's further away. But the next one we come up to right here is going to look more like this, which is actually getting us exceptionally close now to what it is. So it sort of depends, but it's like, suppose our first one, or sorry, our second one had brought us over to like here, let's say, and then that tangent line looks more like this. Well, that's brought us even farther away. And so sometimes it ends up screwing up. So you want to start as close as you can, but generally it will work.
Okay, thank you very much.
Yep. And the good news is if it doesn't work, your calculator will just do the work for you anyway. So, all right. Any other questions on that? All right, let's see if we can use it once then. We're going to use Newton's method to solve x cubed plus 3x minus 5 equals 0. What should we do first?
Pick a value that's going to be close.
All right, pick a value that's going to be pretty close. So how do we decide a value that's going to be pretty close?
We just test it or no?
Well, we can, one way we could use it is that we could use the intermediate value theorem. And we know this function is continuous, right? And so if it's a continuous function and we can find a value that we're below the x-axis and a value that we're above the x-axis, or a value where this is negative and a value where this is positive, that should do it. So let's say at x equals 1, we end up with -1, right? But at x equals 2, we end up with, if we call this f of x equals x cubed plus 3x minus 5, we end up with x equals 2 gives us f of x equals what? What is that? 8 and 6 is 14 minus 5 is 9. Right? True. So we see a sign change there. And if we see the sign change, we know that there must be a root between 1 and 2. So we'll just pick something in between 1 and 2. That makes sense to everybody? Why we would choose something between 1 and 2?
Yes.
Cool. So we'll call our x naught value 1.5 maybe to start with. And unfortunately, my graphing calculator that I'm supposed to be able to use here on my laptop is not working, my like TI-84 one. So I can't type everything out for you and show you how to use your calculator for this. They want me to purchase a license and I'm not going to spend all that money to do that. Even though they claimed that they extended the free trial for the entire school year, but they didn't. So what we're going to do is we're going to write out first the formula, and then I'll work through how to plug it into your calculator. So our formula should be the next guess is always equal to the previous guess minus f of our previous guess divided by the derivative of our function. So what's f prime of x? Just 3x squared plus 3, right? So this should be 3x sub n squared plus 3. And so what we will do is on your graphing calculator, which you all have with you, right? You all have your graphing calculator with you today.
Yes.
All right. On that graphing calculator, you're going to first type in your first guess. So you're going to hit 1.5. And then you're just going to hit enter to store that as your most recently used value. And then you're going to type in with every x sub n equaling answer. You're not going to type in 1.5, you're going to type in answer, which is like second in the negative sign, I want to say. I don't have my calculator. Yeah, second in the negative sign. So what you'll type in, so you'll do 1.5 and then enter, and then you're going to type in answer minus, and then you're going to put two parentheses, one for the full fraction and one for the numerator, and you'll do answer cubed plus 3 answer minus 5, one parenthesis, divided by new parenthesis, 3 answer squared plus 3 parenthesis parenthesis. So that's what you want to type in. When you hit enter, it should give you your next x value. It'll say x sub 1 is, I think it comes out to be like 1.3 repeating. Is that right?
I got 1.205.
Uh-oh.
I did too, 1.205.
Really? Oh. All right. 1.205 what?
128205.
All right. And then all you have to do then, you don't have to type anything else in. You just got to hit enter. And it'll give you a new value. What's your new value?
1.155429527.
Okay. And then hit enter again. What do you get?
One 1.154172278.
And hit enter again. What do you get?
1.154171495.
And hit enter again. Did you get the exact same thing?
Yes.
All right. So we'll say x sub 5 is the same. And so as soon as we get to 9 or 10 decimal points worth of accuracy, where we're repeating the same number again, we know that we are as accurate as our calculator is going to allow us to be. And the approximate intercept of that function, x cubed plus 3x minus 5, is 1.154171495. Good or no?
Beautiful.
Great. And when you do this on your homework, I want to see everything that I'm circling in blue as your work shown. So show me the function, the derivative, explain why it's continuous, explain how you got your first guess, show me all the things that you plugged in, and show me the formula that you used. You don't need to write. You don't need to write what you typed into the calculator or the stuff that you typed in there. Just what's in blue is what I need to see there. Good or no?
Great.
Wonderful. All right. Let's do another one. Let's figure out where these two functions intersect on the interval between 1 and 2. So this time, since I've given you an interval, you don't really need to show me how you got your first guess, since you know you're going to guess something between 1 and 2 to start with. So how do we determine where the two functions intersect? What should we do?
Set them equal to each other.
Yep, so we'll just say sine of x over 2 equals x squared minus 1. And Newton's method is good for finding x-intercepts or finding when something equals 0. So we will just make this x squared minus 1 minus sine of x over 2 equals 0. And that will be the equation that we are looking to solve. That'll be f of x. We'll call it, how about we call it h of x? H of x is that. And what will h prime of x be?
Two x minus cosine x over 2.
Oh, no. 2x minus, you forgot the chain rule.
1/2.
1/2 cosine x minus 2.
1/2 cosine.
My bad.
That's okay. Life will go on probably. All right, so there's our function. Anywhere we see the x's, we're going to replace those with answers. So when we type it in, we're going to type in, well, we'll write out what the full formula is. But anywhere we see the x sub n's, we'll replace those with answers. So we'll have x sub n minus x sub n squared minus 1 minus sine x sub n over 2 over 2x sub n minus 1/2 cosine x sub n over 2. And let's all agree on a good value to start with. What do we want to start on?
1.5.
1.5 sounds good. And plug it all in and tell me what you get eventually. I don't want to write all the other ones down this time, but. Did we get a number or no?
Yeah. 1.284233989.
1.28428, what?
1.284233989.
33989.
Yeah.
I didn't get that value.
I did.
That's what I got for the first one, but are we looking for the last one?
Oh, I was just looking for the last one.
Oh, the last. Okay. I thought we were going in order again.
I didn't want to write them all out this time. All right, let's see. 1.260729771. Does that sound right?
Yep.
All right. And that was what, x was it x sub 4 and 5 again, or?
Five was the same as 4.
Okay, so that was x sub 4, was x sub 5, was this. Perfect. Everybody good there? Any issues with this Newton's method process?
No.
All right, cool. So tonight you will have a homework assignment on Newton's method that is due, I don't know. I guess I could just make it due at the end of the weekend. So that'll be nice for you. Lucky you, it'll be due at the end of the weekend. So that's that on the Newton's method stuff. Now we will continue on and start talking about optimization. So before we get into doing some optimization problems, just want to quickly talk about the steps in the process. So for optimization problems, you need to read the problem, because sometimes I've noted that people don't really read the problem. They just look for a bunch of numbers and like sort of, oh, it's got a pyramid in it and it's got these numbers, and then they just write a bunch of crap out without really reading and understanding what's being asked of you. So make sure you read and read and read and read until you understand. Then draw a picture. Pictures are good, they will be your friend. Write out your equation. If you need to graph the equation, you don't always have to graph the equation, but it's important to look at the domain of your equation that you write. And we're trying to figure out something that's trying to be at a max or something that's going to be at a minimum. So like, what is the maximum profit, or what is the minimum cost, or what is the maximum square footage, or something like that. So we want to determine what's to be maximized or minimized, and then write our equation as a function of that variable. Take your derivative, find the critical values, look at the endpoints, and determine your extrema. Okay. Should be pretty straightforward. Shouldn't be anything too complicated, anything worse than stuff we've done the rest of this year. So we'll start with a nice, easy one here. We want to find the point on the graph of y equals x squared plus 1 that is closest to the point 3, 1. So what are we trying to find here?
Trying to
Don't-
minimize distance.
Oh, good. I was going to say, don't say the point on the graph that is closest to this point. No. We were looking for a minimum distance. So here is x squared plus 1. And here is the point 3, 1. Right. So we are looking at a distance between this point and the function. And what is the distance? The distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. Yeah? Everybody agrees with that? Hopefully.
Yeah.
Okay, cool. So in order to minimize that distance, we need to first write all of this in terms of one variable, whereas I have x2, x1, y2, and y1. I have 4 different variables at the moment. So we're looking for the distance between 2 points. One point is the point 3, 1. And the other point is some arbitrary point on this parabola, which would be some x value. And what's the y value of the parabola in terms of x?
The
X
square root
squared
of
plus 1.
Right, just x squared plus 1.
Oh
Right?
yeah.
So we're looking for the distance between the point 3, 1 and any arbitrary point x comma x squared plus 1, because we know that any x comma x squared plus 1 will fall on this parabola. Good? Okay. So now our distance is the square root of x minus 3 squared plus x squared plus 1 minus 1 squared, or simplified down, this just becomes x squared squared, or x to the 4th, and then x squared minus 6x plus 9. Good? Or no? Not good? Good?
Yeah.
Okay. So from there, we got 2 ways that we can proceed. We've got our equation. We've drawn a picture. We've labeled it. We found our equation. We've written the variable that we want to minimize, d, the distance, in terms of one other variable, x. So now we just need to take our derivative. Now, there's one thing that you can do, which is often very convenient with equations that are square roots, is that the x value at which the square root of something is at a minimum or a maximum is the same x value as when just that thing inside of it is at a minimum or maximum. So it doesn't really help us too much on this problem, but in the future, if you wanted to, you could say this is true and say, well, when is d squared at a minimum or a maximum? The x value at which d squared is at a minimum or maximum is the same x value at which d is at a minimum or maximum. So I'm going to write that off to the side. D and d squared are at max and min at the same x values. And then once you find that x value at which it's at a min or a max, you have to make sure that you're using the appropriate formula, the distance formula again, to find that actual minimum distance if you needed to. Not just the d squared, but you could just minimize d squared to find the correct x value. So let's do that. What is d squared prime? That's right, it's 4x cubed plus 2x minus 6. Very good. Yeah, everybody okay with that?
Yes.
All right, so when is 4x cubed plus, what was it, plus 2x minus 6 equal to 0? 2x cubed plus x minus 3 equals 0, right? Divide them all by 2. God, I hope that factors. Does that factor? Of course it does. Where's my plus? Should be over here, right? Gives us values of what?
-3/2 and 1.
Wonderful.
Wait, isn't it
wait, that's
cubed?
yeah, that's not a quadratic. Oh, that's a cubed, huh? Oops, my bad. Nah, we'll get rid of all that. That's a cubic, not a quadratic. All right, does that factor?
It can be factored into x minus 1 times 2x squared plus 2x plus 3.
Great. 2x squared plus 2x plus 3, you said?
Yeah.
Lovely. And I'm sure you figured that out by using synthetic division with a 1, or just by having the internet factor it for you?
Yeah, synthetic division.
Oh, good. Okay, right. 1 is a possible rational root. Remember, the possible rational roots of this are plus or minus 1 and plus or minus 3 factors of the constant divided by factors of the leading coefficient. So one option is 1, -1, 3, -3, a half, -a half, and 3/2, -3/2. So we chose 1. Bring down the 2, multiply by the 1, add, multiply, add, multiply, add. Comes out to be a 0. So we know it was a perfect factor of it. And that gives us the 2x squared plus 2x plus 3 times the x minus 1. So I know you're all familiar with synthetic division and the rational root theorem. At least you should be. That gives us x equals 1. Oh, good. There's a value that we already had when I factored it the wrong way because I didn't realize it was a cubic instead of a quadratic. And then what about this one? This one, the discriminant is less than 0, right? B squared minus 4ac is less than 0, which tells you that this piece of it has no real solutions. Remember learning that back in like 7th or 8th grade? Hopefully, yeah. Yeah, hopefully so. So we got x equals 1. Make our chart. Our derivative that we used was 4x cubed plus 2x minus 6. For this factorization, plug in, let's say 0, and what do you get? You get a negative times a positive, which gives you a negative, and you plug in something more than 1, like 1,000, and you get a positive and a positive. So you go from decreasing to increasing, telling you have a local minimum at x equals 1. So that tells us that our minimum distance occurs at x equals 1. And then we'll go back in and say, well, what's f of 1? Right, f of 1 is 2. So the point at which that distance is a minimum is the point 1, 2. Good or no?
So good.
Great. Anybody have any questions on that? No? All right, let's do another one. We're going to inscribe a rectangle under the arch of a sine curve and find the largest area the rectangle can have. And then figure out the dimensions and give that area. So I'm going to give you guys a minute or two to sketch a picture and start writing an equation. And then in 2 or 3 minutes, I'll check in with you guys and make sure you're on the right track. And then we'll work through the rest of it together if you're not finished. Ready, go. Or now. We get a good picture?
Yeah.
something like this, right? Where we have y equals sine x, we have one arc of the sine curve, it crosses through here at x equals pi. And we want to find the largest area this could have. So that's going to be a length times a height, or a base times a height, or whatever you want to call it. And we need to figure out how to minimize that area. Area is length times height by writing it all in terms of x. And so x, remember, is always a distance from the origin going this direction. So this distance here we could call x, which would make this height here sine of x. So we'll say height is sine x. And if this is x, since sine curves are symmetric, even though mine doesn't look real symmetric, this would also be x. And that would tell me that the length ought to be pi minus 2x. Is that what you guys got for your dimensions? Or no?
Yes.
Wonderful. So then what?
Take the derivative.
Take the derivative, and we'll have to use the product rule for that, right? So pi minus 2x times cosine x, and then plus negative 2, so negative 2 sine x. And we want to know, when does that equal 0? And through the magic of your calculator, you should be able to tell me when that equals 0. Between 0 and pi, right? Our domain here is only from 0 to pi, non-inclusive. Remember, you can use second calculate x-intercept on your graphing calculator to calculate that x-intercept. All right, Denise says x equals 0.7104627. Sound good to everybody? Good. If you didn't get that, let me know. Is that not what you got? Everybody got that? Hopefully.
Yes, but can't there be two values? Like, I got another value as well.
So what was your other value?
2.4311299.
2.43. Okay. So yeah, that's fine. So if you got x equals 2.43, the problem with that is if I go over 2.43 here, I'm going to be like right here. Right?
Yeah.
Yeah, and so that means that that's the beginning of my rectangle. And that's not actually going to, like this, that means this x also has to be 2.43, which means that I'm not going to really get the same rectangle here. Or I'm not going to get this nice, like, big old rectangle in here, because I can't go over more than half of pi here. So really we could have said the domain, I should have said the domain was 0 to pi over 2, because pi minus 2 times 2.43 is going to give us a negative length. Does that make sense?
Yeah.
Okay. So, just that 0.710. And since you have the derivative already graphed on your graphing calculator, that should make life even easier to do the sign chart. We should hopefully see that to the left of 0.710, it's increasing, or that the derivative is positive, so the function is increasing, and to the right the derivative is negative, so the function is decreasing. And so this would be our x value. And so our height and our length would just be the sine of that value. And then once you've actually evaluated those out, you can approximate them using 3 decimals because we always want to do at least 3 decimals. And so what do you get as your height and as your length when you approximate that out to 3?
I got 0.652 for height and 1.721 for length.
71721?
Yeah, 1.721.
Oh, 1.721. And, it's also asking for the actual area. You can multiply together and get an answer, but that's not a good use of our time, I don't think. Any questions on that?
No.
All right, let's just do one more of these, and then Monday we'll finish up optimization and related rates, and then that'll kind of be the end of our applications of the derivative, and then we can start moving into all of our integration stuff, where I'm going to add a lot of things that we did not learn last year. So you guys want to try and do this one on your own first, and then we'll talk about it?
Yes.
All right, I'll give you guys, what, 5 minutes? That seems like that'll be enough, probably. All right, 5 minutes it is. Ready, go. All right. Hopefully that was enough time there. So we're going to cut these corners off and fold up our sides to make a box with an open top. We started off with this being 20 by 25, and we cut off x from each one. So what are the dimensions of our box when we fold these up? We've got a length of 25 minus 2x, and we've got a height, or we've got a width, let's say, of 20 minus 2x, and we've got a height of what? What's our height become when we fold these each up?
X.
X.
Right.
Yep. So our volume should be, if we distribute all of this out, let's see, what does that come out to be? Should come out to be 4x cubed. What do we get? We get minus 90x squared and plus 500x. Hopefully I distributed that right. Yeah?
Yeah.
Okay. And then from there, we'll just take our derivative, v prime, the 12x squared minus 180x plus 500. And we want to know, when does that equal 0? We could probably simplify that down. Those at least divide by 2. Let's see, they definitely divide by 4. So 3x squared minus 45x plus 125 equals 0. And let's see, I don't know, does that factor out? Did that factor out for you guys or no?
No, you have to use the quadratic equation.
All right, so 45 plus or minus the square root of negative 45 squared plus 4 times 3 times 125 all over 6 should be our x values. And what did that inside the radical simplify to be? 45 plus or minus what? Didn't you guys do this? What did that simplify to inside the radical?
525.
525. All right. And let's see, that'll divide by 5, right? 21 times. And would we use the plus or would we use the minus for that?
Minus.
Yeah, we got to use the minus because if we think back to here, the x value's got to be greater than 0 and less than 10 because I can't cut off more than 10 from each of these sides. So clearly 45 plus 5 root 21 over 6 is going to be more than 10, right? I mean, this is about 25 here, and that would make this about 70. So 70 over 6 is more than 10. So we want to use 45 minus 5 root 21 over 6. And if we were to put that on the sine chart, 0 and 10 here, we would find that when we plugged in our value between 0 and this, so if we plug in like 1 to our derivative, we're going to end up with 3, or is our derivative? We're going to put 12 minus 180 plus 500, which is positive. So positive increasing. And if we plug in something like 9, this is going to be 81 times 12 minus 180 times 9. That's a very big negative. Plus 500 still ends up being negative. So negative, and we end up with a local max. So that's what we want x to be, to have a maximum. And then you would just go plug it in to your volume equation to find the actual maximum volume. Good or no? Any questions on that? Or on optimization in general?
If we do the second derivative test, do we need a sign chart for that as well?
If you did the second derivative test, that's fine. So you could have done that. What do you got? 24x minus 180, right? And then you just plug in your value. That's fine. As long as you should have got that value is negative and then tell you that it's a max. That'd be fine.
Okay, thank you.
Either a sign chart or the second derivative test is good. Just remember that the second derivative test only works if the first derivative is 0 at that point, not if the first derivative is undefined at that point. So, which this one is fine for that, but just keep that in mind if you like to do the second derivative test. All right, that should be it for today. We are done.